Today we will be discussing the importance of heritability. What is heritability? Heritability of a trait within a population is the ratio of variation due to the differences between phenotypic and genetic differences of individuals in a population. Heritability is symbolized as a variance as H2. Heritability is the proportion of additive variation, meaning more than one gene contributes to their phenotype, to phenotypic variation, meaning variation of phenotypes that exist in a population. So the proportion ranges can help us determine what the variation in a population can be. So we can use Breeder's equation to help us determine heritability. So using this equation, we can find if H2 is equal to 0, it would help us determine that genes do not contribute to phenotypic individual differences. If H2 is equal to 1, all differences on a trait reflect genetic variation, meaning environment has no influence. When H2 is equal to 0.5, it means 50% is due to genetics, 50% is due to environment. Heritability graphs can help us estimate the slope of linear correlation between parent and offspring phenotypes on a graph. So the slope determined here gives us H2, which is heritability. So let's look at Breeder's equation. We'll dissect it piece by piece. So let's start with R. R is the difference between mean of an opposing population and the mean of an entire population. So looking at this example, we are given two graphs. The first one shows us the parent average population, which is 4, and in the offspring, we have an average population of 2. So in order to calculate R, we are comparing the parent and offspring's average population. So to find the difference, we would take 4, we would subtract it by 2, and in this case, we'll get 2. So 2 is R in this scenario. So now let's look at S. So let me rewrite. That's not what I want. Let me rewrite Breeder's equation. R is equal to H2S. Okay, so now we are looking at S. S is a selection differential. It is the difference between the mean of reproducers and the mean of entire population. So let's look at this example at the top left-hand corner. We are seeing that the average population is 12. And the average population of reproducers is 10. So in order to find S, we will take 12, we will subtract it by 10, and we should get 2. So in this scenario, S is equal to 2. So let's do a quick example just to make sure we have this down. So as we read, we'll take note of what we do know and what we don't know. African elephants have been bred to increase the width of their tusks. In the current generation, the mean tusk length is 42 inches. If only a subset of this population with the mean tusk length of 52 inches are allowed to reproduce, and the nearest sense heritability of this trait is H2 equal to 0.2. What is the expected tusk length in the offspring generation? We're missing a few words right there. So let me repeat the last sentence. What is the expected tusk length in the offspring generation? So what we do know is that the mean tusk length is 42 inches, and the tusk length allowed to reproduce is 52. So from there, we can subtract 52 by 42. and we get 10. Okay, we know H2 is equal to 0.2. And we know this represents S, the selection differential. So, as the equation that we have discussed, and let me rewrite that. R is equal to H2S. Okay, so we know H is equal to 0.2. S is equal to 10, and that equals 2. Okay, so let's draw out this graph. It might make it easier for us. Okay, it's 52 average. Okay, and in this new offspring generation, we would have 54. And why did we have 54? So, as we have seen, we have discovered that R is equal to 2. We would add 2 to the average offspring's population, and that will give us the expected tusk length in the offspring's generation. Okay, so that wraps up our lecture. In this last slide, we will discuss why is heritability important. So understanding heritability allows us to calculate and determine whether or not selection will be effective in changing the mean value of a trait in population. So calculating heritability and understanding it allows to determine whether evolution occurs or not. So we now know that when H2 does not equal to 0, evolution occurs.